Okay, we're ready to take notes 3D in the Math 4 course. A little teacher humor there. All right, we are going to be using our skills with logarithms and exponentials to solve real-world problems. And along the way, I'm going to be giving you a number of new formulas, or at least new to us. Some of them you may have seen last year in Math 3. But you will need to hang on to these formulas because you will need them for quizzes and tests, not to mention the homework. All right, so let's start out with this formula. If you are going to compound something quarterly, that means 4 times a year, then the formula is going to look something like this. Where n is the number of times per year. Since it is quarterly, n is going to be 4 in this case. And so we'll take our bits and pieces. Now, they want to know, find the amount of time needed to double the money. If our original principal is $5,000, then doubling it would mean $10,000. And we're going to fill in 9%. Please, please, please remember to move your decimal 2 places. And quarterly means a 4 goes underneath. And quarterly means a 4 goes up there. And we want the amount of time, so t is what we are searching for. So I've got everything up there except for t. I got to get t by itself. I've got to get t away from that exponential. Well, first of all, we're going to divide both sides by 5,000. That's going to give us 2. And by the time I divide 0.09 divided by 4, I get this. And I'm going to go ahead and move the 2 over to this side. It's more convenient with what we've been doing. We're going to turn this around and rewrite it as a log of base 1.0225 raised to the 4t goes over there is 2. And so this we can rewrite as log 2 over log 1.0225, changing it from a log of base 1 point yada yada to base 10 in both cases. And I'm going to come up with something for that out of my calculator. All right, I'm going to get 31 and some change out of that. And I'm going to leave the 31 decimal in there because I'm just going to turn around and divide it by 4, which means I get 7.7879. I might as well call it about 7.8. But now here's something important that we need to talk about. When a bank is going to compound something quarterly, that only happens 4 times a year. Now that is not a continuous function. That is more like a step. It's like, you know, if I were to graph this, your balance is here, and then it's here, and then it's here, and then it's here. What they like to call a step function. And it's like you get a solid dot here and an open one there, and a solid dot here and an open one there, that sort of thing. That is what your bank account is actually doing in this case. And so you really haven't gained any money during the entire quarter until you reach the end of the quarter. So if I say 7.75, that's a year and 3 quarters. That's a year and 9 months. But this said like 7.78 something, which means it's gone past that. It's going to require more than just the 7 years and 9 months. So we're going to go ahead and round it up and say t is going to equal 8 years. Because it's going to be 8 years, that 8th year, that quarter at the end of the year before you actually see the double. Because if you stop at 7 years, 9 months, it's going to be just short of doubling. It won't quite reach there. All right, here, there's another word that changes the whole tone of this thing. That is compounded continuously. That means that our formula is going to look like this. And yes, that's the E as in natural log E. And so when we're kind of using the same players, just at a different rate. So we want to know how long is it going to take to reach 10,000 when you start with 5,000 times E raised to the 0.09 T. We don't know what T is yet. We don't know. And in this case, because it's continuously, there's no sense of steps in this. It really is a smooth curve moving upward. And so you can have fractions and decimals involved in the year. So if we're going to kind of mirror the same tactics we used earlier, we're going to divide both sides by 5,000. I'm going to move my 2 over here so that it's easier to read, because when I'm going to rewrite it as a logarithm, it's going to be log base E. The exponent goes over here, and the 2 goes there. Well, log base E, that's natural log of 2. So I can go and figure out what the natural log of 2 is, and then eventually divide it by 0.09. So the natural log of 2 is about 0.7. And then when I divide that by 0.09, I wind up with about 7.7 years. It's like 7.7016. So it's you're okay to round it there. And because the curve is continuous, I don't have to worry about quarters or months or days or anything like that. It's just in one smooth upward curve. Now, you've heard about banks talking about APY, annual percentage yield, and they're trying to, sell themselves above their competitors, that they're going to offer you more money if you put it in their bank. And so annual percentage yield basically says that if I'm talking about earning 6% a year, but I'm compounded daily, then I'm actually earning a little better than 6%. Here's the rule of thumb for APY. You do it for $1 for 1 year. Now you plug that into the formula. Now we're still using the same formula. But this time we're going to say $1. Our rate is 6%. Compounded daily is 365. And again, we're doing it for just 1 year. Now, I will warn you about something. When you punch in 0.06 divide 365, you are going to get an ugly decimal. Matter of fact, you're going to get one of those decimals that says E-4. Well, think for just a second. Once you divided 0.06 by 365, what's your next move? Add 1, right? Plus 1. And you're no longer staring at an E-4 in your calculator. So just go ahead and push through it and see if it'll get you past that E business. Now, whatever that is, I'm going to raise to the 365th power. Is basically 1.000164, yada, yada, yada. to the 365th power. So once I do raise that, I get 1.06183 and then some. Now here's the thing. Once you've gotten this far with it, the one in front, let me get a color going here. This one right here represents the principal. You know, if you say 1 times the principal, you get the principal back, right? And so this one right here represents the part of the principal that never went away. This, however, represents everything else that got added on to the principal once you got finished doing your interest. So if this represents everything at the end of 1 year on $1, then you want to re-express it as a percentage, which means that the decimal place goes there. And we're going to say 6.18% APY. Most of your banks generally do a percent with 2 decimal places on the end, like 6.25% interest on your CD or something like that. So 6.18% APY. So what's going to happen is that I may ask you a question saying, here are 4 situations. Choose the one that gives you the best APY, and you'll have to actually run the numbers on all of them. That sounds very much like a test question. But anyway, the rule of thumb, APY, $1 for 1 year, and run the rest of the numbers. Now, when we start getting into things like population growth, they're not compounding daily or anything like that. They're usually doing things 1 year at a time. So your formula is going to be a more of a simplified version of this, 1 plus r to the t. So if we're asking, you know, if we start with 6.1 billion now, and we're going to reach 122 billion, I'm going to do this in terms of billions. I'm going to say 122 here and 6.1 there, realizing that when I get my number, this is in billions. Now, if I go in there and I say, all right, 1.4%, that's 0.014. And the time is the thing we want to figure out. So now we approach it like we would any other problem. So we would want to simplify the parenthesis first. Then we would want to divide both sides by 6.1. This actually works out nicely to 20. I'm going to bring the 20 over there because we're going to turn around and write this as a logarithm. Log base 1.014 to the t goes over there, 20 goes in the middle. And by the time that I say log 20 over log of 1.014, I should be able to punch that in and figure out what it is. Okay, and the calculator says that this should be 215.475. Now, let's talk about this a minute. This is another one of those real-world situations when they ask, when will it reach 122 billion? Now, when they talk about the year 2000, you might as well say January 1st. You know, because if my time is 215.475, that's almost 215 and a half years. You're talking May or June of that year. And there's nothing in the problem that really allows you to make that kind of a distinction. So the thing is, if you're talking about 2215, the year, we haven't reached 122 billion yet. So you're going to have to go to the next year. It's going to be 2216 when you actually reach the 122 billion and cross that mark. You will have done that by January 1st, 2216, and not by 2215. It would happen somewhere in the middle of the year. And since we don't have the ability to distinguish that specifically, we'll just say by 2216, you've got your 122 billion. Okay. All right. Now we're starting a culture with 10,000 bacteria. And the thing is that it doubles. Now the formula is going to look something like this. But it doubles every 40 minutes. And if T is in minutes, then if I said, all right, so what's it look like at the end of 40 minutes? It should have doubled just once, not 2 to the 40th power. So what we're going to do is we're going to do that. If it's every 40 minutes, we're going to put that underneath the T. Now, if I say what happens after 40 minutes, well, it's 40 over 40, that's 2 to the 1. And it will double once, which is what I wanted. After 80 minutes, it will double twice. So now let's set up a formula, a function that starts with 10,000 bacteria and does this. So that's our formula. Now we can move on to answer some of the other questions. So find the number of bacteria after 1 hour. So we'll say 10,000 times 2 raised to the 60 over 40. That's 10,000 times 2 to the 1.5. And that's going to give us 28,284.27. So we might as well just call it that many bacteria. Now, if I wanted to turn this around the other way and say, when will I find 50,000? 50,000 is my answer. I started with 10,000, and I don't know how much time it took. So this is where we'll use some of our other solving skills and say 10,000 divided on both sides. It's going to give me 5 equals 2 to the t over 40. And I'm going to move my 5 to the other side because I'm getting ready to write it as a logarithm. Log base 2, exponent goes over here, 5 goes there. Well, this I can rewrite log 5 over log 2 equals t over 40. That's going to give me about 2.32. And if I multiply both sides, excuse me, no. I got to multiply both sides by 40. I get 92.8. I might as well say 93. And those were minutes. So after 93 minutes, I'll have my 50,000. Now, when you think about it, it's a healthy thing to back up and consider it mentally and ask, does this answer make sense? If I started with 10,000 and it doubles every 40, that means after 40 minutes, I'd have 20,000. After 80 minutes, I'd have 40,000. And 50,000 is not much past that, and 93 is not much past 80 minutes. So yeah, this answer does seem to make sense. Now, the rest of this, I'll tell you what, I'm going to break here and pick this up on the other side because we've got half-life and we've got Newton's law of cooling. So I'm going to cut this into 2 videos.